is continuing section 7.2. You have now learned the definition of the Laplace transform and applied it to learn some patterns. So we've practiced those in homework. You have also learned and practiced the inverse Laplace transform, so please be sure that you've completed both of those portions of the assignment before watching this one. Now what we'll do is put that together and learn how to solve differential equations. So I'm going to continue with examples. This is the second half of 7.2 in the ZIL textbook. You'll recall that I looked at the Laplace transform of a function and how, on this right side, what that was equivalent to, as well as a higher order derivative. Now this pattern continues, and in my last set of slides I showed you for higher order derivatives. In this set of slides I'm only going to use up to that second derivative, so I'm just reminding you of these. If you don't have this in the notebook, I would jot this down before I start this video. These would be used, and when you complete homework, you would use these so frequently that you would probably have this memorized. Something to help you memorize this, so Laplace transform of a function. So function, the Laplace transform here, I have s linear, so s times that, minus f, because this was f of t, of 0. For the second order derivative, you'll know the power. Notice the power goes up. You'll multiply this by s, and you'll have minus the first derivative 0. So look at those patterns to try to help you memorize this. You'll use this quite a bit. What we're about to do are solve two differential equations, or two sets. So I'm going to solve a differential equation of this type. You'll notice that you have constant coefficients. This is actually a simplified version of what was on your last test. I'll show you why it's simplified. I didn't want to do the whole differential equation yet until you've practiced some other problems. So this is simplified a bit, and this is a second differential equation also from your test that we'll be looking at. So I don't have your initial conditions on this slide, but we'll be using some initial conditions with this as well. So here's our first problem. 2y prime minus 4y prime minus 6y is equal to a constant 5 under these conditions. What we'll do is apply the Laplace transform to both sides. So now we're going to try to solve a differential equation. Applying the Laplace transform to both sides, remember it is a linear operator. So when you take the Laplace transform on the left, you can divide this. It'll be 2 times that term, the second order derivative, minus y L times the Laplace transform of the first derivative minus 6 times the Laplace transform of y. That's equal to, you don't have to pull the 5 out. You know that the Laplace transform of 5 is 5 over s. I did go ahead and just use that constant rule consistently through there. Apply the rules that we discussed. So the Laplace transform of the second derivative you see here in purple, and I multiply everything by 2, minus 4 the Laplace transform of y prime, and I have that here in blue, so y prime, the Laplace transform of y prime here. Minus 6 times the Laplace transform of y, so we'll use the capital Y notation, is equal to 5 over s, and that would come from your practice understanding Laplace transforms of constants. If this were a different function, you'll need to know how to take the Laplace transform of various functions that you practiced in 7.1. Now, this really just comes down to algebra, and sometimes the algebra is difficult. We're going to combine like terms on the left-hand side. So you'll notice I have a 2s squared y of s. Here what I've done is factored out the y of s. So anything with a y of s I've combined right here. So 2s squared. Right here I see a negative 4s. So you'll notice I have a negative 4s. I factored out the 2. And the negative 6ys, here's your negative 6ys right here. 2 times negative 3. Now, if it didn't have a y of s, I threw it over to the right side. Why? Well, we're solving an equation, just like in algebra. So I want to solve for y of s. So you'll notice anything with a y of s I've left on the left-hand side. I factored out y of s. On the right-hand side, I have a 5 over s. These extra terms, so the negative 2s y of 0, negative 2s on the other side becomes positive 2s y of 0. I also had a 2y prime. You'll notice it's here. I had a positive 4y of 0 thrown on the other side. That becomes a negative 4y of 0. This may be hard to tell. This is in purple. It is from this 2s, and this is in blue. It is from this 4s. I'm sorry, this negative 4 times y is 0 right there. So now that I have this, I want you to think, okay, in algebra, how would you go about solving this? And do we have any information to simplify this also? So up here, let's go ahead and use our initial conditions. You'll notice this is a reason that Laplace transform is very helpful if you do have initial conditions. If you don't, then these constants would honestly be quite messy to deal with from here. But because we have those initial conditions, this term completely cancels, and this just becomes 2. You'll notice on the left-hand side I've also factored. S squared minus 2s minus 3 becomes s minus 3s plus 1. This is equal to 5 over s plus 2. The 2 comes from this term after plugging in the initial condition. And I should mention again, if any of this is too fast, the nice thing about video is please pause this and take time to work through each of those steps. I realize you may just be watching this to get an idea to work another homework problem though, and so I also don't want to go too slow for those of you that are just trying to look back at one or two things. Once I get to this point, I want to solve for y of s. I'll simply divide both sides by these factors, the product 2s minus 3s plus 1. And that will give you something like this. So you'll notice one thing that I skipped on my slides to fit all of this on my slides. I did two things here. I divided by this product, and I also combined, I combined these two terms. So 5 over s plus 2s over s gives me 5 plus 2s over s. I divided by 2s minus 3s plus 1, and so I have something that looks like this. Now, I want to use what I learned in the beginning of 7.2 and apply the inverse Laplace transform. Using the inverse Laplace transform, I will have to divide this up using partial fraction decomposition. So by divide, I mean I will have to decompose this rational expression so that I have terms where I can apply the inverse Laplace transform. Currently, I cannot in this current form. That won't be too bad since I have all linear factors. Again, another reason I simplified this from the test example. Because I have linear factors, I'll be able to split this up into a over s plus b over s minus 3 plus c over s plus 1, as you see here. Now I highly suggest that you pause the video at this point and try to get these constants yourself. But for a, I found negative 5/6, b was 11/24, and c 3/8. From this expression, I am now able to apply inverse Laplace transform functions. So this first one, what I'm going to do is take the inverse Laplace transform of every term. So y of s, I'll have y of t here. This, when I apply the inverse Laplace transform, will simply be the constant negative 5/6. Here I have 11/24 times e to the 3t, 3/8 e to the negative t, and this would be my solution for y of t. Now if that was too fast, I apologize, and I just ask that you go back through those 3 slides and try that again. I have assigned 3 problems that will relate to this. I'm going to keep going and talk about systems. Now this will not appear in your homework this week, but the ideas I felt like I could go ahead and throw into this lesson. This is actually another section, a few sections later in this chapter, but this is a test problem from your last test that I felt like you guys could understand this at this point already. It doesn't use any techniques from 7.3, and so we could go ahead and do this problem. This is a system of equations, so what I'll have to do is apply the Laplace transform, and I'll apply the Laplace transform to both statements. So x prime becomes what you see here on the left is equal to x of s minus 2y of s. Y prime, as given here, is equal to 2x of s minus y of s. Now I have a system, and you might think of this as a system of linear equations, like in algebra. I'm going to have to solve this somehow. you'll notice I went ahead and substituted my initial values so that I just have those constants filled in. So 500, 100. That was given to you in your last test in a predator-prey model. Now what I will do, and you could do this different ways, but what I'm about to do, I believe I set up the slides where I solved the first one for capital X of s, the Laplace transform of x of t. So here from the left equation, I combined all the terms with x of s. So I got anything with an x of s on the left, anything without on the right. When I got all of the Laplace transforms of x on the left, you'll notice I was able to factor it out and I had an s minus 1. So I took the right hand side and divided by s minus 1. You might be thinking right now, why did she not combine those fractions? I battled with that a bit in the video, but I chose to not do that here because a couple steps in the future might be easier with it in this form. Once I have this, I'm going to use that, so here's the exact expression from the last one, and substitute it into the second equation. So in case that was too fast, I solve this for x of s, the Laplace transform of x. I'm now plugging that in to the second equation. That will give me an equation entirely in terms of y of s. You'll notice there's a y of s on the left and a y of s on the right, however, so I did have to do some algebra to get those on the same side. Once they are on the same side, I combined the terms on the left, and in that set of parentheses, I got common denominators. So this is from the last slide, getting common denominators. I go ahead and I multiply everything out on the top and simplify. When I multiply on the top, I get s squared minus s plus 4s, so that will give me a plus 3s, minus 4 plus 4. The 4's will cancel. S squared plus 3s factors to give me s times the quantity s plus 3. On the right, you'll notice that I did get common denominators here. The reason I waited before is because it saved me one step perhaps in my explanation, and I thought that might make a clearer explanation. There's no need to leave those separate fractions now. Here I'll get common denominators. It'll make my life easier. So by getting common denominators, you'll notice you had 1000, you'll have plus 100s minus 100, so that is where the 900 came from. I got common denominators and combined these two terms. Now, to solve for y of s, you will multiply both sides by the reciprocal of this rational expression. The s minus 1's cancel, and you will end up with this numerator. You'll notice I factored out the 100 over this as your denominator. Splitting that up using partial fraction decomposition. So I recommend you pause the video here. This was a basic case, and again, if you do not like that cover-up method that I discussed, you will start seeing that these will take quite a bit of time, and so that practice that I've done in class with the cover-up method is to help you with these. If you refuse to do that, that is absolutely fine, but your work will take longer. Your homework will take you longer, and I don't want that to seem so overwhelming. So just keep those things in mind. I just don't want it to be overwhelming, but to be honest, these problems, you can't avoid it. So, alright, using partial fraction decomposition, once you finish that, if you'll notice, y of s, the Laplace transform of y of t, is equal to this right side, and that is pretty easy to take the inverse of. This will simply be 300 minus 200 e to the negative 3t. So there's our solution for y of t. Now I wish I could say that x of t was a piece of cake after that. We have to do a little bit of algebra. So this was a statement I had before. Because I now have y of s, that is at the top of the slide, I plug that in. And the algebra takes a bit, so 2 times 300 is negative 6. I'll have a negative 600. 2 times negative 200, or negative, since this is negative 2 times negative 200, that's where the positive 400 came from. And I multiplied the denominators as necessary. So So I have something like this on the right hand side. If I want to take the inverse Laplace transform, I need to decompose the second and third fraction, or rational expression. When I do that, so you'll notice I have the first term left, it remains. 600 over s times s minus 1 has broken into these two. 400 over s minus 1s plus 3 I now have here. Because 3 of these terms have the same denominator, you'll notice 500 minus 600 plus 100, those all cancel. 600 over s plus 100, or I'm sorry, minus 100 over s plus 3 is all that remains. And fortunately, that is a piece of cake to take the inverse Laplace transform of. So 600 minus 100 e to the negative 3 are all that remain. If you look at your last exam, you'll notice that this was on your previous exam. If you peeked at my solutions to the last exam, you actually saw another method that you don't quite understand yet, but we will discuss in the next chapter. What I did here in this video is did this using Laplace transforms. So ultimately, by May, there will be 3 different methods that you could use to solve that predator-prey model. Thank you for your time. Best of luck with your work. Let me know if you have any questions.